Hello everyone, welcome. Today we're going to talk about element number 92, uranium. It is impossible to discuss uranium without acknowledging that the first atomic weapon used in anger was a uranium fission bomb, built in secret deep in the deserts of New Mexico and detonated over the unsuspecting city of Hiroshima on the Honshu Island of Japan. Hiroshima, a modern city on Japan's Honshu Island, was largely destroyed by an atomic bomb during World War II. Today, Hiroshima Peace Memorial Park commemorates the 1945 event. In the park are the ruins of Genbatu Dome, one of the few buildings that was left standing near Ground Zero. Other prominent sites include Shuke-en, a formal Japanese garden, and Hiroshima Castle, a fortress surrounded by a moat and a park. The Great Wall of China and the Apollo moon shot were large undertakings, but measured by its irreversible consequences for the whole planet and by the sheer leap of faith required to attempt it, nothing yet wrought by the hand of man compares to the Manhattan Project. The scientists who built the uranium bomb were so sure it would work, they didn't even bother testing it, although they had only enough U-235 for one bomb, a fact that was one of the most closely guarded of all nuclear secrets. The Trinity test, carried out at Alamogordo 21 days earlier, proved the feasibility of one more complex plutonium-based design of the Fat Man dropped on Nagasaki 3 days after Hiroshima. Nagasaki is a Japanese city on the northwest coast of the island of Kyushu. It's set on a large natural harbor with buildings on the terraces of surrounding hills. It is synonymous with a key moment during World War II, after suffering an Allied nuclear attack in August of 1945. The event is memorialized at the city's Atomic Bomb Museum and Peace Park. Whether mankind will survive the invention of the atomic bomb remains an open question. Though nuclear weapons have been used in war only twice, uranium itself has become commonplace in recent wars around the world. Naturally occurring uranium is 99.28% uranium-238 and 0.71% uranium-235. Both isotopes are radioactive, but only the U-35 can be used to make fission bombs. When uranium is processed for bomb making, about 2/3 of the uranium-235 is taken out. What's left is called depleted uranium, or DU. Uranium-235, seen here, is an isotope of uranium. Since the most common isotope of uranium is 238, it means that that one is the most stable. Uranium-235 has 3 less neutrons than uranium-238, and the neutrons act as the glue that keep the nucleus together and stable. So without that glue keeping the nucleus together, uranium-235 is found in less quantities in the universe due to its radioactivity and instability. Let's learn about some information. Uranium-235. Uranium-235 is an isotope of uranium making up about 0.72% of natural uranium. Unlike the predominant isotope, uranium-238, it is fissile, i.e., it can sustain a nuclear reaction. It is the only fissile isotope that exists in nature as a primordial nuclide. Uranium-235 has a half-life of 703.8 million years. So every, 703.8 million years or so, half of uranium-235 is gone. Uranium-235 has 92 protons. The number of neutrons are 143, according to MIT.edu. Its alpha is 4.679. Its decay products is 231 thorium. It decays into thorium-231, and its symbol is 235U. It can be pronounced as uranium-235 or U-235. Fat Man is the codename for the type of nuclear bomb that was detonated over the Japanese city of Nagasaki by the United States on August 9th of 1945. It was the second of the only 2 nuclear weapons ever used in warfare, the first being Little Boy, and its detonation marked the 3rd nuclear explosion in history, according to Wikipedia. DU is widely used not for its remaining radioactivity, but simply because it is a very hard, very dense metal that makes excellent armor-piercing projectiles. Tungsten, element number 74, similarly dense, can be used as well, but if you're the government of a nuclear state, you have a lot of leftover DU on hand from making bombs. And DU has the added advantage of catching fire on impact. What is depleted uranium used for? Depleted uranium is used for tank armor, armor-piercing bullets, and as weights to help balance aircrafts. Depleted uranium is both a toxic chemical and radiation health hazard when inside the body, because it's a heavy metal like lead or mercury. When not dealing death, uranium can be found on eBay and in the kitchens of antique collectors the world over. Fiestaware plates and bowls made prior to 1945, especially the orange ones, contain so much uranium in their glaze that they will set off Geiger counters from several feet away. Eating from them is a bad idea, not so much because of the radioactivity, which is the relatively harmless alpha type, which means that 2 protons and 2 neutrons, a helium nuclei, but because uranium, like lead, as previously mentioned, is a heavy metal poison that can leach out of the glaze on contact with acidic foods. Possession of up to 15 pounds of natural uranium or thorium, element number 90, is perfectly legal for private individuals, so radioactive fiestaware can be and is widely sold, collected, and used legally. Some fiestaware and certain other types of pottery made in the early to mid 20th century are radioactive because uranium was used to make the colored glazes. Intact dishes do emit radiation but aren't harmful. However, the risk of exposure increases if the pottery is chipped or cracked. According to thoughtco.com. According to the author, true story. A colleague at my software company has a kitchen full of fiestaware, and she eats off of it every day. After borrowing his Geiger counter, she now stores one particularly hot set of bowls slightly further away from the sink. Leaving uranium, we say goodbye to the naturally occurring elements. From here on out, the elements exist on Earth only at the pleasure of mankind, which means that we make them. The first of this new breed is Neptunium, which I already made a video about. If you're interested in learning about Neptunium, I'll leave a link in the description below. Other than that, let's continue with uranium. Uranium-238. Uranium-238 is the most common isotope of uranium found in nature with a relative abundance of 99%. Unlike uranium-235, it is non-fissile, which means it cannot sustain a chain reaction in a thermal neutron reactor, according to Wikipedia. Its protons are 92, its decay products are thorium-234, its symbol is 238U, and its parent isotopes are presented here. Its parent isotopes are Pu-242, plutonium, and Pa-238, proactinium. Its spin is 0, and its half-life is 4.468 times 10 to the power of 9 years, significantly longer than the half-life of uranium-235, which has a half-life of 703.8 million years. That is equal to about 4.468 billion years. You may ask, how do I detox my body of metal, specifically heavy metals? Some foods can help you detoxify by getting rid of heavy metals from your body. These foods bind to the metals and remove them in the digestive process. Heavy metal detox foods to eat include cilantro, garlic, wild blueberries, lemon water, spirulina, cholera, barley grass juice powder, and Atlantic dose, according to healthline.com. Trinity was the code name of the first detonation of a nuclear weapon. It was conducted by the United States Army at 5:29 a.m. on July 16, 1945 as part of the Manhattan Project, according to Wikipedia. Its location was Jornada del Muerto. Its date was July 16, 1945. Here we have its yield. It's even in a movie called Trinity and Beyond, the atomic bomb movie. The Manhattan Project was a research and development undertaking during World War II that produced the first nuclear weapons. It was led by the United States with the support of the United Kingdom and Canada, according to Wikipedia. Its start date was August 13, 1942, in the midst of World War II, and its end date was August 1945, at the end of World War II. Included in the event is World War II. Here we have tantalum, element number 73. I previously made a video on the element tantalum. Here's some more information. Tantalum, element number 73. I'm one exotic dude. I come from the Democratic Republic of the Congo in Africa, but you'll often find me much closer to home. I'm used to store, charge, and even out the current in almost every miniature electronic device you can think of, even the ones you're probably using to watch this video right now. I'm totally corrosion resistant and one of only 2 metals used for replacement body parts. Tantalizing. Tantalum's date of discovery was in 1802. Its density is 16.65 grams per centimeters cubed. Its melting point is 3017 degrees Celsius or 5463 degrees Fahrenheit. Its boiling point is 5458 degrees Celsius or 9856 degrees Fahrenheit. Its chemical symbol is Ta. Some more information. Tantalum, element number 73, Ta. This transition metal gets its name from Tantalus, a figure in Greek mythology. Tantalum does not corrode easily and is used to make capacitors, which are tiny devices for storing electricity inside cell phones and tablets. Its atomic mass is 180.948. Its state is a solid. Its discovery was in 1802 by Anders Gustav Ekberg, which I talked more about in the tantalum video. Feel free to click on the link in the description below. Microlite is so named because it forms tiny crystals. Here we have dark crystals of microlite and ore of tantalum in rock. Now let's get back to our regularly scheduled program. Uranium, element number 92. The actinoid elements. Its symbol is U, its atomic number is 92, its atomic weight is 238.03, its color is gray, its standard state is solid at 25 degrees Celsius or 77 degrees Fahrenheit. Its classification is metallic. I am a powerful force of nature. Fire a neutron at my unstable radioactive form, atomic number 235, and my nucleus splits with a roar of energy, firing neutrons in all directions and starting a chain reaction that rips me apart. Control this reaction, called nuclear fission, and I generate power, but pack me into a bomb and I can flatten whole cities. Uranium's date of discovery was in 1789, way before tantalum. Its density is 19.05 grams per centimeters cubed. Its melting point is 1132.2 degrees Celsius or 2070 degrees Fahrenheit. Its boiling point is 3900 degrees Celsius or 7101 degrees Fahrenheit. Italian-American physicist Enrico Fermi leads a U.S. team that builds the world's first nuclear fission reactor. In 1945, the first atomic bomb is dropped on Hiroshima. Uranium is a very important element because it provides us with nuclear fuel used to generate electricity in nuclear power stations. Uranium is a very important element because it provides us with nuclear fuel used to generate electricity in nuclear power stations. It is also the major material from which other synthetic transuranium elements are made. Naturally occurring uranium consists of 99% uranium-238 and 1% uranium-235. Uranium-235 is the only naturally occurring fissionable fuel. So essentially a nuclear explosion is a catalyzation of the decomposition of uranium-235 because it only exists in small quantities because it decomposes way more quickly than uranium-238. When we create a nuclear explosion, we are catalyzing the decomposition process of uranium-235. Also when we use it for nuclear reactors, such as in this submarine right here. Uranium-235 is the only naturally occurring fissionable fuel, a fuel that can sustain a chain reaction. Uranium fuel used in nuclear reactors is enriched with uranium-235. The chain reaction is carefully controlled using neutron absorption materials. The heat generated by the fuel is used to create steam to turn turbines and generate electrical power. Here we have nuclear energy. Nuclear reactions are a highly efficient way of releasing energy. Smashing atomic particles together sets off a chain reaction, producing enough heat to generate large amounts of electricity. I previously talked about this page in a previous video, but here we have some more information. In a breeder reactor, uranium-238 captures neutrons and undergoes negative beta decay to become plutonium-239. This synthetic fissionable element can also sustain a chain reaction. The extra neutrons become protons and increase the atomic number of uranium-238 to plutonium-239. This synthetic fissionable element can also sustain a chain reaction. Uranium is also used by the military to power nuclear submarines and in nuclear weapons. Here we have a nuclear submarine. A nuclear submarine is a submarine powered by a nuclear reactor, but not necessarily nuclear armed. Nuclear submarines have considerable performance advantages over conventional submarines, according to Wikipedia. Uranium is located here on the periodic table. U is here. You are here. What is a breeding reaction? Nuclear energy has a remarkable property. Some nuclear reactors are designed to produce more fuel than it consumes. This extraordinary technique is known as breeding, according to radioactivity.eu.com. Energy sources. People in the industrialized world use a lot of energy in homes, business, and industry for travel and transportation. The energy used comes from primary sources such as fossil fuels, nuclear energy, and hydropower. Crude oil, natural gas, and coal are called fossil fuels because they were formed over millions of years by heat from the Earth's core and pressure from rock on the remains, fossils of plants and animals. Non-renewable sources. Fossil fuels are limited resources on our planet which create greenhouse gases and toxic pollutants. Nuclear energy produces fewer greenhouse gases but leaves harmful waste, radioactive material that remains radioactive for a long time. Not that the uranium wasn't radioactive to begin with, it just creates other elements that are radioactive and have different types of half-lives. They are more radioactive and emit more frequently alpha, beta, and gamma radiation, which makes them harmful after the electricity is created. Crude oil, liquid hydrocarbons found deep underground. Natural gas, hydrocarbon gas formed millions of years ago. Coal, solid hydrocarbons made by heat and pressure. Nuclear energy, energy released by splitting uranium atoms. Depleted uranium is uranium that has much less uranium-235 than natural uranium. Essentially, somebody depleted the natural uranium from most of its U-35 and left mostly U-38. It is considerably less radioactive than natural uranium because its half-life is longer and its nucleus is relatively more stable. It is a dense metal that can be used as ballast for ships and counterweights for aircraft. It is also used in ammunition and armor. Nuclear requirements for moderator graphite. The slowing down of neutrons results principally from energy transfer during elastic collisions between the neutrons and the moderator atoms. For a material to be an efficient moderator, the collision rate per unit volume must be relatively high, according to nucleus.iaea.org. What does graphite do to neutrons? What does graphite do in advanced gas-cooled reactors? The graphite bricks act as a moderator. They reduce the speed of neutrons and allow a nuclear reaction to be sustained, according to edfenergy.com. Here we have uranium hexafluoride, consisting of 1 atom of uranium and 6 atoms of fluorine. If you're interested in learning about the element fluorine, I'll leave a link in the description below. Why is depleted uranium armor-piercing? Depleted uranium is roughly 0.7 times as radioactive as natural uranium, and its high density makes it ideal for armor-piercing rounds, such as the PGU-14 and certain tank shells. Depleted uranium is also used to reinforce certain types of armor and has a number of non-military uses, such as ballasts in ships, according to WashingtonPost.com. Uranium compounds have been used as coloring agents for ceramics. Uranium hexafluoride, UF6, 1 atom of uranium combined to 6 atoms of fluorine, is a solid with an unusual high vapor pressure, 115 torr or 0.15 atmospheres or 15,300 pascals, at 25 degrees Celsius or 77 degrees Fahrenheit. UF6, uranium hexafluoride, is chemically very reactive, but despite its corrosive nature in the vapor state, UF6 has been widely used in the gas diffusion and gas centrifuge methods of separating uranium-235 from uranium-238. Uranium is a dense, hard metallic element that is silvery white in color. It is ductile, malleable, and capable of taking a high polish. In air, the metal tarnishes and when finely divided, breaks into flames. It is a relatively poor conductor of electricity. Though discovered in 1789 by German chemist Martin Heinrich Klaproth, who named it after the then recently discovered planet Uranus. The metal itself was first isolated in 1841 by French chemist Eugene Melanchthon Peligot by the reduction of uranium tetrachloride with potassium. Uranium is a dense, hard metallic element that is silvery white in color. It is ductile, malleable, and capable of taking a high polish. In air, the metal tarnishes and when finally divided, breaks into flames. It is a relatively poor conductor of electricity. Though discovered in 1789 by German chemist Martin Heinrich Klaproth, who named it after the then recently discovered planet Uranus, the metal itself was first isolated in 1841 by French chemist Eugene Melanchthon Peligot by the reduction of uranium tetrachloride, UCl4, with potassium. Here we have the unbalanced and balanced formula. The formulation of the periodic system by Russian chemist Dmitry Mendeleev in 1869 focused attention on uranium as the heaviest chemical element, a position that it held until the discovery of the first transuranium element, neptunium, in 1940. In 1869, the French physicist Henri Becquerel discovered in uranium the phenomena of radioactivity, a term first used in 1898 by French physicists Marie and Pierre Curie. This property was later found in many other elements. It is now known that uranium, radioactive in all its isotopes, consists naturally of a mixture of uranium-238, 99.27%, which has a 4,510,000,000 year half-life, uranium-235, 0.72%, which has a 713 million year half-life, and uranium-234, which consists of 0.006% of the total uranium, which has a 247,000 year half-life, which is why it exists in even less proportions, because its half-life is shorter. These long half-lives make determinations of the age of the Earth possible by measuring the amounts of lead, uranium's ultimate decay product, in certain uranium-containing rocks. Uranium-234, one of the daughters of the radioactive uranium decay series, uranium-235 is the parent of the actinium decay series. Certain alloys of depleted uranium are also found in armor for tanks and other military vehicles. Because of its very high density, uranium metal is well suited for this purpose as well as for armor-piercing projectiles. Uranium. This heavy metal was the first substance to be identified as radioactive, a discovery made by the French physicist Henri Becquerel in 1896. It is used in the making of nuclear bombs and as fuel for nuclear reactors, which generate electricity. Its atomic mass is 238.029. Its state is a solid, and its discovery was in 1789 by Martin Heinrich Klaproth and in 1841 by Eugene Peligot. Here we have a chunk of pure uranium. Those discoveries led to the first self-sustaining nuclear chain reaction on December 2nd, 1942, the first atomic bomb test on July 16, 1945, and the first atomic bomb dropped in warfare on August 6, 1945. The first atomic bomb dropped in warfare on August 6, 1945, the first atomic-powered submarine in 1955, and the first full-scale nuclear-powered electrical generator in 1957. Here we have some information on Antoine-Henri Becquerel. He was born in 1852 and he died in 1908. Born into an illustrious French family of scientists, Henri Becquerel studied at the École Polytechnique in Paris, where he specialized in investigating the properties of light, such as polarization and phosphorescence. In 1892, he became the third member of his family to occupy the chair in physics at the famous Paris Museum of Natural History, and it was here that he made his landmark discovery. The SI unit of radioactivity, equivalent to 1 nuclear decay per second, is named the Becquerel in his honor. The first medical X-ray. One of the most famous images in photographic history, this X-ray of the hand of Röntgen's wife Anna clearly shows her bones and wedding ring. The image was taken in December of 1895 and immediately revealed the medical implications. Fractured bones were being X-rayed by January of 1896, only 1 year later. In the Middle Ages, the mineral pitchblende uranium oxide U3O8 sometimes turned up in silver mines, and in 1789, Martin Heinrich Klaproth of Berlin investigated it. He dissolved it in nitric acid and precipitated a yellow compound when the solution was neutralized. He realized it was the oxide of a new element and tried to produce the metal itself by heating the precipitate with charcoal, but failed. It fell to Eugene Peligot in Paris to isolate the first sample of uranium metal, which he did in 1841 by heating uranium tetrachloride, seen here, with potassium. The discovery that uranium was radioactive came only in 1896 when Henri Becquerel in Paris left a sample of uranium on top of an unexposed photographic plate. It caused this to become cloudy, and he deduced that uranium was giving off invisible rays. Radioactivity had been discovered. The German chemist Martin Heinrich Klaproth is credited with discovering the element uranium in 1789 in a sample of pitchblende. Klaproth named the new element after the planet Uranus, which had been discovered in 1781. It was not until 1841, however, that the French chemist Eugene Melchior Pelegot showed that the black metallic substance obtained by Klaproth was really the compound uranium dioxide. Pelegot prepared actual uranium metal by reducing uranium tetrachloride with potassium metal. Prior to the discovery and elucidation of nuclear fusion, the few practical uses of uranium, and these were very small, were in the coloring of ceramics and as a catalyst in certain specialized applications. Today, uranium is highly valued for nuclear applications. Both military and commercial and even low-grade ores have great economic worth. Uranium metal is routinely produced by means of the AMS process developed by the American chemist F.H. Spedding and his colleagues in 1942 at the Iowa State University, Ames. The AMS process. The AMS process is a process by which pure uranium metal is obtained. It can be achieved by mixing any of the uranium halides with magnesium metal powder or aluminum metal powder, according to Wikipedia. In this process, the metal is obtained from uranium tetrafluoride by thermal reduction with magnesium. If you're interested in learning about the element magnesium, I'll leave a link in the description below. I previously made a video on that element. Uranium is a dense, hard metallic element that is silvery white in color. It is ductile, malleable, and capable of taking a high polish. In air, the metal tarnishes, and when finally divided, breaks into flames. It is a relatively poor conductor of electricity. Here we have some information on uranium. Uranium, element number 92, it's used for nuclear power, it's used for the military, and it's used for nuclear bombs. Nuclear power. Uranium fuels nuclear power plants. 1 kilogram of uranium-235 produces as much energy as 1.5 million kilograms of coal, also known as carbon. Dense depleted uranium is used in shielding, the neels of boats, and in armor-piercing weaponry. Nuclear bombs. The first nuclear bomb used in World War II used enriched uranium-235 as its nuclear fuel, according to the Royal Society of Chemistry. Here we have a pitcher made from green uranium Vaseline glass. The tiles behind the drinking fountains in the Art Deco grade school attended by the author and his children contain significant amounts of uranium in their glaze. The lighter colored ones read over 1,000 counts per minute. Here we have an image of the Nagasaki plutonium bomb printed using uranium-salted photo paper. This print is actually radioactive. Red Fiesta ware, made prior to 1942, is famously radioactive, but other colors and brands are as well. A gold-colored titanium nitride coating protects the depleted uranium inside this small bullet from oxidation. Because this nuclear reactor fuel pellet contains uranium enriched in U-235, it is not legal to possess without a license. The element uranium becomes the subject of intense study and broad interest after German chemists Otto Hahn and Fritz Strassmann discovered in late 1938 the phenomena of nuclear fission in uranium bombarded by slow neutrons. Here we have some information on Otto Hahn, Enrico Fermi, Marie Curie, Leo Szilard, Fritz Strassmann, Herbert L. Anderson, and Frederick Joliot-Curie. Italian-born American physicist Enrico Fermi suggested in early 1939 that neutrons might be among the fission products and could thus continue the fission as a chain reaction. American physicist Leo Szilard, American physicist Herbert L. Anderson, French physicist Frederick Joliot-Curie, and their co-workers confirmed in 1939 this prediction. Later investigation showed that an average of 2.5 neutrons per atom are released during fission. As you can see here, a neutron bombards uranium-235, an isotope of uranium, to create cesium-140 and rubidium-92, and 2 neutrons, on average 2.5. Here we have an image of cesium and rubidium. When these are generated, they would be radioactive. Enrico Fermi was an Italian physicist and the creator of the world's first nuclear reactor, the Chicago Pile 1. He has been called the architect of the nuclear age and the architect of the atomic bomb. He was one of very few physicists to excel in both theoretical physics and experimental physics, according to Wikipedia. Jean-Frédéric Joliot-Curie was a French physicist and husband of Irene Joliot-Curie, with whom he was jointly awarded the Nobel Prize in Chemistry in 1935 for their discovery of induced radioactivity. Otto Hahn. Otto Hahn was a German chemist who was a pioneer in the fields of radioactivity and radiochemistry. He is referred to as the father of nuclear chemistry and father of nuclear fission. Hahn and Lise Meitner discovered radioactive isotopes of radium, thorium, proactinium, and uranium, according to Wikipedia. Leo Szilard was a Hungarian-German-American physicist and inventor. He conceived the nuclear chain reaction in 1933, patented the idea of a nuclear fission reactor in 1934, and in late 1939 wrote the letter for Albert Einstein's signature that resulted in the Manhattan Project that built the atomic bomb, according to Wikipedia. Friedrich Wilhelm Strassmann was a German chemist who, with Otto Hahn in December of 1938, identified the element barium as the product of the bombardment of uranium with neutrons, according to Wikipedia. Herbert Lawrence Anderson was an American nuclear physicist who was professor of physics at the University of Chicago. He contributed to the Manhattan Project, according to Wikipedia. The first atom bomb. On July 16th, 1945, a huge fireball rose into the skies above the Alamogordo test range in the New Mexico desert. The Trinity test was the culmination of decades of research on atomic structure and the nature of radioactivity. With energy equivalent to 16,000 tons of TNT, this was the first artificial nuclear explosion, herald of a new technology that would transform the world for good or ill. As early as 1919, physicist Ernest Rutherford had shown that it was possible to trigger transmutations from one element to another artificially by bombarding a material with alpha particles, which is the helium nuclei without its electrons. It was clear that splitting the atom could release enormous energy, but scientists had no idea how this might be done in practice on a large scale. Then, in 1932, came confirmation of the existence of the neutron, followed by the realization that bombardment with high-energy neutrons was a powerful way to trigger radioactive decay and release further neutrons in the process. In 1933, Hungarian-born physicist Leo Szilard suggested that, in the right conditions, a densely packed critical mass of radioactive material could undergo a chain reaction with neutrons from one decay event, triggering others and potentially releasing a huge amount of energy. Certain elements were known as potential sources of radioactive emissions, and in the mid-1930s, experiments by the Joliot-Curies and Enrico Fermi successfully created artificial radioactivity by bombarding stable heavy elements with alpha particles, again helium nuclei. In 1938, German physicist Otto Hahn discovered an isotope of barium produced by the breakdown of uranium. His former student, Lise Meitner, and her nephew, Otto Frisch, showed how this could be the result of nuclear fission, the breaking apart of heavy isotopes to form much lighter ones. This fission of heavy elements clearly offered the potential for Szilard's chain reaction. On the brink of World War II, eminent physicists urged the U.S. President Franklin Delano Roosevelt to obtain this technology before Germany did. The resulting Manhattan Project brought together many of the finest minds in 20th century physics, under the scientific direction of American physicist J. Robert Oppenheimer, to figure out the practicalities of nuclear reactors and weaponry and the means of refining and concentrating fissile material. The test detonation was watched in secrecy by fewer than 300 people, but people all around the world were to see images of the mushroom cloud over Hiroshima, Japan, just 3 weeks later. A quote by Robert J. Oppenheimer: "I am become death, the destroyer of worlds." The gadget. The first offspring of the Manhattan Project was known as the gadget, shown here with U.S. physicist Norris Bradbury. This makeshift-looking device was covered in conventional explosives that, when detonated, compressed the core of plutonium to reach a critical density. So what is a neutron? The neutron is a subatomic particle with symbol N, or N with a 0, which has a neutral charge and a mass slightly greater than that of a proton. Protons and neutrons constitute the nuclei of atoms, according to Wikipedia. The neutron was discovered by James Chadwick in 1932. Uranium, U, radioactive chemical element of the actinoid series of the periodic table, atomic number 92. It is an important nuclear fuel. Uranium constitutes about 2 parts per million of Earth's crust. Some important uranium minerals are pitchblende, impure U3O8, uranite, UO2, carnotite, a potassium-uranium vanadate, autunite, a calcium-uranium phosphate, and torbernite, a copper-uranium phosphate. Some important uranium minerals are pitchblende, which is U3O8, seen here, uranite, UO2, seen here. Uranite, formerly pitchblende, is a radioactive uranium-rich mineral and ore with a chemical composition that is largely UO2, but because of oxidation, typically contains variable proportions of U3O8. Radioactive decay of the uranium causes the mineral to contain oxides of lead and trace amounts of helium, which is due to the accumulation of electrons from alpha decay emissions. Carnotite is a potassium-uranium vanadate radioactive mineral with chemical formula K2UO2 times 3H2O. The water content can vary, and small amounts of calcium, barium, magnesium, iron, and sodium are often present, according to Wikipedia. Consists of the elements potassium, uranium, oxygen, vanadium, and hydrogen. Autunite with formula CaUO22PO42 times 1012H2O is a yellow-greenish fluorescent phosphate mineral with a hardness of 2 through 2 plus 1/2. Autunite crystallizes in the orthorhombic system and often occurs as tabular square crystals, commonly in small crusts or in fan-like masses, according to Wikipedia. Autunite consists of the elements calcium, uranium, oxygen, phosphorus, and hydrogen. I previously talked about the elements calcium and phosphorus if you're interested in learning about those elements. I'll leave a link in the description. And finally, torbernite, a copper-uranium phosphate. Torbernite, whose name derives from the Swedish chemist Torbern Bergman, is a radioactive hydrated green copper uranyl phosphate mineral, found in granites and other uranium-bearing deposits as a secondary mineral. It is also known as chalcolite. Torbernite is isostructural with the related uranium mineral autunite, according to Wikipedia. Torbernite consists of the elements copper, uranium, oxygen, phosphorus, and hydrogen. I previously made a video on copper if you're interested in learning about that element. These and other recoverable uranium ores as sources of nuclear fuels contain many times more energy than all the known recoverable deposits of fossil fuels. 1 pound of uranium yields as much energy as 1.4 kilograms or 3 million pounds of coal. Uranium occurs naturally in several minerals such as uranite, pitchblende, brannerite, and carnotite. It is also found in phosphate rock and monazite sands. World production of uranium is about 41,000 tons per year. Extracted uranium is converted to the purified oxide known as yellow cake. Uranium metal can be prepared by reducing uranium halides with group 1 or group 2 metals or by reducing uranium oxides with calcium or aluminum. Here we have the actinides. Elements in the actinide series, such as uranium, are unstable and radioactive. The heat released by uranium atoms can be used for generating power. Here, fuel rods packed with uranium are used in nuclear reactors. Fission occurs with slow neutrons in the relatively rare isotope uranium-235, the only naturally occurring fissile material, which must be separated from the plentiful isotope uranium-238 for its various uses. Here we have uranium-238 with a half-life of 4.47 billion years. Uranium-238 decays through the release of an alpha particle, losing 2 protons and 2 neutrons to produce thorium-234. Here we have thorium-234. As a neutron in the nucleus transforms into a proton, thorium-234 undergoes beta decay. It has a half-life of 24 days. The atom emits an electron and a neutrino as it is transmuted into practinium-234. With a half-life of 6.7 hours, practinium-234 decays again through beta emission. Because 2 neutrons have now been converted to protons, the product of this decay is uranium-234. Uranium-234. More stable than its 2 predecessors in the decay chain, uranium-234 has a half-life of 245,500 years. It undergoes alpha decay to produce thorium-230. Thorium-230. Also relatively stable, thorium-230 decays through alpha emission to create radium-226 with a half-life of 75,380 years. Radium-226. With a half-life of 1,602 years, radium-226 changes into radon-222 through alpha decay. Radon-222. Less stable than its predecessor, radon-22, has a half-life of 3.8 days and decays through another alpha emission into polonium-218. Polonium-218. With a half-life of just 3.1 minutes, this isotope decays rapidly. Almost all polonium-218 undergoes an alpha emission to produce lead-214, but a small fraction, 0.02%, undergoes beta decay and follows a slightly different decay chain at this point. Lead-214. This isotope undergoes beta decay with a half-life of 26.8 minutes, producing bismuth-214. Bismuth-214. An isotope with a half-life of 19.9 minutes, nearly all bismuth-214's atoms undergo beta decay to produce polonium-214, but 0.02% take a different route through alpha decay to become thallium-210. Polonium-214. With an extremely short half-life of 0.16 milliseconds, polonium-214 decays by alpha emission to produce lead-210. Lead-210. Beta emission is how lead-210 decays to produce bismuth-210. Its half-life is 22.3 years. Bismuth-210. All but a tiny fraction of this decays by beta emission. It has a half-life of just a little over 5 days. Here we have polonium-210. This has a half-life of 138 days. And here we have lead-206. This stable isotope marks the end of the decay chain. All the various side branches of the decay chain also eventually reach lead-206. Uranium-238, however, after absorbing neutrons and undergoing negative beta decay, is transmuted into the synthetic element plutonium, which is fissile with slow neutrons. Natural uranium, therefore, can be used in converter and breeder reactors in which fission is sustained by the rare uranium-235 and plutonium is manufactured at the same time by the transmutation of uranium-238. Fissile uranium-233 can be synthesized for use as a nuclear fuel from the non-fissile thorium isotope thorium-232, which is abundant in nature. Uranium is also important as the primary material from which the synthetic transuranium elements have been prepared by transmutation reactions. Uranium, which is strongly electropositive, reacts with water. It dissolves in acid, but not in alkalis. The important oxidation states are +4, as in the oxide UO2, tetrahalides such as UCl4, and the green aqueous ion U4+. The important oxidation states are +4, as in the oxide UO2, tetrahalides such as UCl4, and the green aqueous ion U4+, and +6, as in the oxide UO3, the hexafluoride UF6, and the yellow uranyl ion UO2 2+. In an aqueous solution, uranium is most stable as the uranyl ion, which has the linear structure OUO2+. Uranium also exhibits a +3 and a +5 state, but the respective ions are unstable. The red U3+ ions oxidizes slowly even in water that contains no dissolved oxygen. The color of the UO2+ ion is unknown because it undergoes disproportionation. UO2+ is simultaneously reduced to U4+ and oxidized to UO2 2+, even in very dilute solutions. Uranium compounds have been used as coloring agents for ceramics. Uranium hexafluoride UF6 is a solid with an unusually high vapor pressure. 115 torrs, or 0.15 atmospheres, or 15,300 pascals, at 25 degrees Celsius or 77 degrees Fahrenheit. UF6 is chemically very reactive, but despite its corrosive nature in the vapor state, UF6 has been widely used in the gas diffusion and gas centrifuge methods of separating uranium-235 from uranium-238. UF6 is chemically very reactive, but despite its corrosive nature in the vapor state, UF6 has been widely used in the gas diffusion and gas centrifuge methods of separating uranium-235 from uranium-238. Organometallic compounds are an interesting and important group of compounds in which there are metal-carbon bonds linking a metal to organic groups. Uranosine is an organouranium compound, UC8H82. In which a uranium atom is sandwiched between two organic ring layers related to cyclooctatetraene. Its discovery in 1968 opened a new era of organometallic chemistry. Uranium hexafluoride is an inorganic compound with the formula UF6. Uranium hexafluoride is a volatile white solid that reacts with water, releasing corrosive hydrofluoric acid, HF. The compound reacts mildly with aluminum, forming a thin layer of aluminum trifluoride, AlF3, that resists any further reaction from the compound, according to Wikipedia. Organometallic OM chemistry is the study of compounds containing and reactions involving metal-carbon bonds. The metal-carbon bond may be transient or temporary, but if one exists during a reaction or in a compound of interest, we're squarely in the domain of organometallic chemistry, according to chem.libretexts.org. The reaction of uranium metal with anoxic liquid water is highly exothermic and produces stoichiometric uranium dioxide, UO2, and hydrogen. The reaction apparently proceeds through a uranium hydride intermediate that can sequester part of the hydrogen during the initial reaction, according to www.pnnl.gov. What is nuclear transmutation? Nuclear transmutation is the conversion of one chemical element or an isotope into another chemical element. Nuclear transmutation occurs in any processes where the number of protons or neutrons in the nucleus of an atom is changed, according to Wikipedia. Uranium processing. Preparation of the ore for use in various products. Uranium, U, although very dense, 19.1 grams per cubic centimeter, is a relatively weak, non-refractory metal. Indeed, the metallic properties of uranium appear to be intermediate between those of silver and other true metals and those of the non-metallic elements, so that it is not valued for structural applications. The principal value of uranium is in the radioactive and fissionable properties of its isotopes. In nature, almost all 99.27% of the metal consists of uranium-238. The remainder consists of uranium-235, 0.72%, and uranium-234, 0.006%. Of these naturally occurring isotopes, only uranium-235 is directly fissionable by neutron irradiation. However, uranium-238, upon absorbing a neutron, forms uranium-239, and this later isotope eventually decays into plutonium-239, a fissile material of great importance in nuclear power and nuclear weapons. Another fissile isotope, uranium-233, can be formed by neutron irradiation of thorium-232. Even at room temperature, finely divided uranium metal reacts with oxygen and nitrogen. At higher temperatures, it reacts with a wide variety of alloying metals to form intermetallic compounds. Solid solution formation with other metals occurs only rarely owing to the singular crystalline structures formed by uranium atoms. Between room temperature and its melting point of 1,132 degrees Celsius or 2,070 degrees Fahrenheit, uranium metal exists in three crystalline forms known as the alpha, beta, and gamma phases. Transformation from the alpha to the beta phase occurs at 668 degrees Celsius or 1,234 degrees Fahrenheit, and from the beta to the gamma phase at 775 degrees Celsius or 1,400 427 degrees Fahrenheit. Gamma uranium has a body-centered cubic BCC crystal structure, while beta uranium has a tetragonal structure. The alpha phase, however, consists of corrugated sheets of atoms in a highly asymmetrical orthorhombic structure. This anisotropic or distorted structure makes it difficult for the atoms of alloying metals to substitute for uranium atoms or to occupy spaces between uranium atoms in the crystal lattice. Only molybdenum and niobium have been observed to form solid solution alloys with uranium. The Earth's crust contains about 2 parts per million uranium, reflecting a wide distribution in nature. The oceans are estimated to contain 4.5 times 10 to the power of 9 tons of the element. Uranium occurs as a significant constituent in more than 150 different minerals and as a minor component of another 50 minerals. Primary uranium minerals found in magnetic hydrothermal veins and in pegmatites include uranite and pitchblende, the latter a variety of uranite. The uranium in these two ores occurs in the form of uranium dioxide, which, owing to oxidation, can vary in exact chemical composition from UO2 to UO2.67. Other uranium ores of economic importance are autunite, a hydrated calcium uranyl phosphate, torbernite, a hydrated copper uranyl phosphate, coffinite, a black hydrated uranium silicate, and carnotite, a yellow hydrated potassium uranyl vanadate. It is estimated that more than 90% of known low-cost uranium reserves occur in Canada, South Africa, the United States, Australia, Niger, Namibia, Brazil, Algeria, and France. About 50 to 60% of these reserves are in the conglomerate rock formations of Elliott Lake, located north of Lake Huron in Ontario, Canada, and in the Witwatersrand goldfields of South Africa. Sandstone formations in the Colorado Plateau and the Wyoming Basin of the western United States also contain significant reserves of uranium. Uranium ores occur in deposits that are both near surface and very deep, e.g., 300 to 1,200 meters or 1,000 to 4,000 feet. The deep ores, sometimes in seams as thick as 30 meters. As in the case with ores of other metals, surface uranium ores are readily mined with large earth-moving equipment, while deep deposits are mined by traditional vertical shaft and drift methods. Uranium ores typically contain only a small amount of uranium-bearing minerals, and these are not amenable to smelting by direct pyrometallurgical methods. Instead, hydrometallurgical procedures must be used to extract and purify the uranium values. Physical concentration would greatly reduce the load on hydrometallurgical processing circuits, but none of the conventional benefaction methods typically employed in mineral processing, e.g., gravity, flotation, electrostatics, and even hand sorting, are generally applicable to uranium ores. With few exceptions, concentration methods result in excessive loss of uranium to tailings. The hydrometallurgical processing of uranium ores is frequently preceded by a high-temperature calcination step. Roasting dehydrates the clay content of many ores, removes carbonaceous minerals, oxidizes sulfur compounds to innocuous sulfates, and oxidizes any other reductants that may interfere in subsequent leaching operations. Roasted uranium ores are leached of their uranium values by both acidic and alkaline aqueous solutions. For the successful operation of all leaching systems, uranium must either be initially present in the more stable hexavalent state or be oxidized to that state in the leaching process. Acid leaching is commonly performed by agitating an ore-leach mixture for 4 to as long as 48 hours at ambient temperature. Except in special circumstances, sulfuric acid is the leachant used. It is supplied in amounts sufficient to obtain a final leach liquor at about pH of 1.5. Sulfuric acid leaching circuits commonly employ either manganese dioxide or chlorate ion to oxidize the tetravalent uranium U4+ to the hexavalent uranyl ion UO2 2+. Typically about 5 kilograms or 11 pounds of manganese dioxide or 1.5 kilograms of sodium chlorate per ton suffice to oxidize tetravalent uranium. In any case, the oxidized uranium reacts with the sulfuric acid to form a uranyl sulfate complex ion, UO2 SO4 3 4-. Uranium ores that contain significant amount of basic minerals such as calcite or dolomite are leached with 0.5 to 1 molar sodium carbonate solutions. Although a variety of reagents has been studied and tested, oxygen is the uranium oxidant of choice. Typically, candidate ores are leached in air at atmosphere pressure and at 75 degrees to 80 degrees Celsius, or 167 degrees to 175 degrees Fahrenheit, for periods that vary with the particular ore. The alkaline leachant reacts with uranium to form a readily soluble uranyl carbonate complex ion, UO2 CO3 3 4 negative, seen here. Prior to further processing, solutions resulting from either acidic or carbonate leaching must be clarified. Large-scale separation of clays and other slimes is accomplished through the use of effective flocculants, including polyacrylamides, guar gum, and animal glue. Animal glue is an adhesive that is created by prolonged boiling of animal connective tissue in a process called rendering. In addition to being used as an adhesive, it is used for coating and sizing, in decorative composition ornaments, and as a clarifying agent, according to Wikipedia. Guar gum, also called gorgon, is a galactoman polysaccharide extracted from guar beans that has thickening and stabilizing properties useful in food, feed, and industrial applications. The guar seeds are mechanically dehusked, dehydrated, milled, and screened according to application, according to Wikipedia. The complex ions UO2, CO3 3 4 negatives can be sorbed from the respective leach solutions by ion exchange resins. These special resins, characterized by their sorption and elution kinetics, particle size, stability, and hydraulic properties, can be used in a variety of processing equipment, e.g., fixed bed, moving bed, basket resin in pulp, and continuous resin in pulp. Conventionally, sodium and ammonium chloride or nitrate solutions are then used to elute the sorbed uranium from the exchange resins. Uranium can also be removed from acidic or leach liquors through solvent extraction. In industrial methods, alkophosphoric acids, e.g., di-2-ethylhexyl phosphoric acid, and secondary and tertiary alkyl amines are the usual solvents. As a general rule, solvent extraction is preferred over ion exchange methods for acidic leachates containing more than 1 gram of uranium per liter. Solvent extraction is not useful for recovery of uranium from carbonate leach liquors, however. Prior to final purification, uranium present in acidic solutions produced by the ion exchange or solvent extraction processes described previously or above, as well as uranium dissolved in carbonate or leach solutions, is typically precipitated as a polyuranate. From acidic solutions, uranium is precipitated by addition of neutralizers such as sodium hydroxide, magnesia, or most commonly, aqueous ammonia. Uranium is usually precipitated as ammonium diuranate, NH4 U2O. From alkaline solutions, uranium is most often precipitated by addition of sodium hydroxide, producing an insoluble sodium diuranate, Na2U2O7. It can also be precipitated by acidification to remove carbon dioxide and then neutralization to remove uranium, or by reduction to less soluble tetravalent uranium. In all cases, the final uranium precipitate, commonly referred to as yellow cake, is dried. In some cases, e.g., with ammonium diuranate, the yellow cake is ignited, driving off the ammonia and oxidizing the uranium to produce uranium trioxide, UO3, or the more complex triuranium octide, U3O8. In all cases, the final product is shipped to a central uranium purification facility. Yellow cake. Yellow cake is a type of uranium concentrate powder obtained from leach solutions, in an intermediate step in the processing of uranium ores. It is a step in the processing of uranium after it has been mined, but before fuel fabrication or uranium enrichment, according to Wikipedia. Refining of yellow cake. Uranium meeting nuclear grade specifications is usually obtained from yellow cake through a tributyl phosphate solvent extraction process. First, the yellow cake is dissolved in nitric acid to prepare a feed solution. Uranium is then selectively extracted from this acid feed by tributyl phosphate diluted with kerosene or some other suitable hydrocarbon mixture. Finally, uranium is stripped from the tributyl phosphate extracted into acidified water to yield a highly purified uranyl nitrate, UO2, NO3, 2. Conversion and isotopic enrichment. Uranyl nitrate is produced by the ore processing operations described previously or above, as well as by solvent extraction from irradiated nuclear fuel. In either case, it is an excellent starting material for conversion to uranium metal or for eventual enrichment of the uranium-235 content. Both of these routes conventionally begin with calcining the nitrate to UO3 and then reducing the trioxide with hydrogen to uranium dioxide, UO2. Subsequent treatment of powdered UO2 with gaseous hydrogen fluoride, HF, at 550 degrees Celsius or 1025 degrees Fahrenheit produces uranium tetrafluoride, or UF4, and water vapor as in the following reaction. UO2 plus 4HF produces UF4, 1 atom of uranium with 4 atoms of fluorine, and 2 molecules of water. Here we have uranyl nitrate consisting of UO2, NO3, 2. Uranyl nitrate is a water-soluble yellow uranium salt with the formula UO2, NO3, 2 times NH2O. The hexa, tri, and dihydrates are known. The compound is mainly of interest because it is an intermediate in the preparation of nuclear fuels. Uranyl nitrate can be prepared by reaction of uranium salts with nitric acid. The hydrofluorination process is usually performed in a fluidized bed reactor. Conversion to uranium metal is accomplished through the AMS process, in which UF4 is reduced with magnesium at temperatures exceeding 1,300 degrees Celsius or 2,375 degrees Fahrenheit. In an often used modification of the AMS process, calcium metal is substituted for magnesium. Because the vapor pressure of magnesium metal is very high at 1,300 degrees Celsius, the reduction reaction is performed in a refractory-lined, sealed container or bomb. Bombs charged with granular UF4 and finely divided Mg, the latter in excess, are heated to 500 to 700 degrees Celsius, or 930 to 1300 degrees Fahrenheit, at which point an exothermic heat-producing reaction occurs. The heat of reaction is sufficient to liquefy the conversion contents of the bomb, which are essentially metallic uranium and a slag of magnesium fluoride, MgF2. Here we have the formula. UF4 plus 2Mg produces 1 mole or 1 atom of uranium and 2 moles of MgF2. Again, here we have the AMS process. When the bomb is cooled to ambient temperature, the massive uranium metal obtained is, despite its hydrogen content, the best quality uranium metal available commercially and is well suited for rolling into fuel shapes for nuclear reactors. Uranium tetrafluoride can also be fluorinated at 350 degrees Celsius or 660 degrees Fahrenheit with fluorine gas to volatile uranium hexafluoride, UF6, which is fractionally distilled to produce high-purity feedstock for isotopic enrichment. Any of these several methods, gaseous diffusion, gas centrifugation, liquid thermal diffusion, can be employed to separate and concentrate the fissile uranium-235 isotope into several grades, from low enrichment 2 to 3% uranium-235 to fully enriched 97 to 99% uranium-235. Low enrichment uranium is typically used as fuel for light water nuclear reactors. After enrichment, UF6 is reacted in the gaseous state with water vapor to yield hydrated uranyl fluoride, UO2F2 times H2O. Hydrogen reduction of the uranyl fluoride produces powdered UO2, which can be used to prepare ceramic nuclear fuel. In addition, UO2 obtained from the enriched UF6 or from UF6 that has been depleted of its uranium-235 content can be hydrofluorinated to yield UF6, and the tetrafluoride can then be converted to uranium metal in the AMS process. The non-fissile uranium-238 can be converted to fissile plutonium-239 by the following nuclear reactions. In this equation, uranium-238, through the absorption of a neutron, N, and the emission of a quantum energy, known as a gamma ray, becomes the isotope uranium-239, the higher mass number reflecting the presence of one more neutron in the nucleus. Over a certain period of time, 23.5 minutes, this radioactive isotope loses a negatively charged electron or beta particle, B. The loss of a negative charge raises the positive charge of the atom by 1 proton, so that it is effectively transformed into the element neptunium, Np, with an atomic number of 93, one more than uranium. If you're interested in learning about the element neptunium, I'll leave a link in the description below. Neptunium-239, in turn, undergoes beta decay, being transformed into plutonium-239, atomic number 94. Uranium and plutonium are recovered from irradiated nuclear fuel through the widely practiced plutonium-uranium extraction or PUREX process. In this solvent extraction process, the fuel cladding encasing nuclear fuel elements, typically made of aluminum, magnesium, or zirconium alloys, is removed either chemically or mechanically, and the metal or oxide fuel is dissolved in nitric acid. Plutonium and uranium are then co-extracted into a tributyl phosphate solution, while practically all the fission products and non-radioactive components are left in the aqueous raffinate. The loaded organic extractant is contacted with an aqueous phase containing any of several possible reductants to separate the plutonium from the uranium, and the uranium is stripped from the tributyl phosphate solution into a dilute nitric acid solution. Additional extraction strip cycles are performed as needed with the separated uranium and plutonium streams in order to complete purification from each other and from traces of co-extracted fission product, zirconium, and ruthenium. Purified uranium nitrate is calcined to an oxide, either UO3 or U3O8, for subsequent conversion to UF6 and enrichment of the uranium-235 content, as described above or previously. Purified plutonium nitrate is converted to plutonium dioxide, PuO2, either for conversion to plutonium metal, weapons-grade plutonium, or for recycling into nuclear reactor fuel. Like uranium, metallic plutonium is usually obtained by high-temperature reduction of a halide salt, plutonium tetrafluoride or plutonium trifluoride, with calcium metal. Much use is also made of the so-called direct oxidation reduction process, whereby PuO2 is reduced with calcium metal to plutonium metal and a calcium oxide slag. Here we have the formula. PuO2 plus 2Ca creates Pu plus 2CaO. Here we have some more information. Plutonium tetrafluoride. We'll talk more about that in the plutonium video. We have plutonium nitrate. PUREX is a chemical method used to purify fuel for nuclear reactors or nuclear weapons. PUREX is a de facto standard aqueous nuclear reprocessing method for the recovery of uranium and plutonium from used nuclear fuel. It is based on liquid-liquid extraction ion exchange, according to Wikipedia. Here we have plutonium oxide, plutonium 4 oxide, PuO2. The metal and its alloy. Reactor grade uranium. Uranium metal, intended for use in production reactors to produce plutonium-239, is rolled into round billets, typically 23 centimeters or 9 inches in diameter and 51 centimeters long. Metallic uranium fuel elements for power reactors are prepared by hot extrusion of the uranium into tubing made of zirca alloy, a corrosion-resistant alloy of zirconium and tin. Uranium fuel elements can also be clad in alloys of magnesium and aluminum. Uranium reacts with a large variety of other metals to form intermetallic compounds, solid solutions, or, in a few instances, true alloys. Many of these systems have been exploited to prepare reactor fuels that possess increased resistance to in-reactor corrosion and radiation damage, as well as greater mechanical strength than pure uranium metal. Examples include low-enrichment uranium molybdenum and uranium aluminum alloys. Even though uranium and plutonium are completely miscible, the plutonium-uranium system is not suitable for nuclear applications. As described above or previously, uranium exists in 3 crystal structures between ambient temperature and its melting point of 1132 degrees Celsius or 2070 degrees Fahrenheit. Plutonium metal undergoes 5-phase transformations below its melting temperature of 640 degrees Celsius or 1183 degrees Fahrenheit. Transformation from one phase to the next occurs no matter what the concentration of either element, thereby preventing use of plutonium-uranium alloys over a major temperature range. However, the addition of zirconium, for example, in a fuel containing 20% plutonium, 10% zirconium, and 70% uranium can yield a metallic system completely adaptable to reactor use. Depleted uranium. Uranium fuel elements can be sheathed in a metallic blanket containing, for example, 10% zirconium and 90% uranium depleted of its uranium-235 content. The depleted uranium, consisting almost completely of uranium-238, captures neutrons that are emitted in the fission of the fuel elements, thus producing or breeding plutonium-239 simultaneous with the generation of nuclear power. Certain alloys of depleted uranium are also found in armor for tanks and other military vehicles. Because of its very high density, uranium metal is well suited for this purpose as well as for armor-piercing projectiles. Pellets made of low enrichment UO2 are universally employed as fuel in commercial light water reactors that produce electrical energy. The pellets are made by blending appropriate quantities of enriched and natural or depleted UO2 powders, mechanically compacting them, adding an organic binder, pressing into pellets, heating to burn off the binder, and finally sintering at high temperature to 95% theoretical density. Fuel pins are fabricated by loading the pellets into a zirca alloy tube. Similar procedures are employed to fabricate mixed uranium-plutonium dioxide (MOX) pellets for use in fast neutron breeder reactors. Unirradiated MOX fuel typically contains 20 to 35% plutonium dioxide. Here's a brief summary of how a nuclear power plant works. We have the uranium decomposing, producing heat, and then it heats up water. The radioactive H2O heats up the non-radioactive H2O. So they're in separate containers. Here we have the separate water. The heat changes the H2O from liquid to a gas. The gaseous H2O has kinetic energy to turn the turbine attached to the generator. And then the generator is a magnet that spins relative to coils moving electrons. Seen here? After the gaseous water turns the turbine, the energized gaseous H2O is cooled down with cooler H2O to be recycled again to be reheated again. And finally, the finale, although not exciting, is still essential. Carbide fuels. Various uranium and plutonium carbides are known, including the monocarbides UC, PUC, UC, PUC, the sesquicarbides U2C3, PU2C3, and the dicarbides UC2, PuC2. Because they are highly refractory, these compounds have been much investigated for use as fuels for nuclear reactors. For example, the fuel in the high-temperature gas-cooled reactor, HTGR, consists of highly enriched uranium, together with thorium as a fertile material, each in the form of carbide pellets embedded in a dense form of graphite. Nitride fuels. Uranium forms a mononitride, UN, and two higher nitride phases, alpha and beta sesquinitrides, U2N3 alpha and U2N3 beta, whereas plutonium forms only a mononitride. Both uranium and plutonium nitrides are brittle, refractory compounds that melt at temperatures generally above 2000 degrees Celsius or 3600 degrees Fahrenheit. This latter property makes the mononitrides attractive as possible high-performance nuclear reactor fuels. So how is uranium explained in X minutes or less in as a short amount of time as possible? Once again, if you like this video, make sure to like, comment, and subscribe. Stay tuned for the upcoming videos on curium, neodymium, and proactinium. Other than that, thank you everyone for watching. Have a great one.